So now we start the problem number 61. Once again, we have spheres and all that. It says that a particle of mass m, mass is given, is kept on the top of a smooth sphere. So we know where the mass is. Mass is here. A particle of mass m. Its mass is m. And the sphere is of radius r. So this radius is fine. Now here it is given a sharp impulse which gives it a horizontal speed v. That means this is given a speed v. Speed v. In the earlier examples, the mass was simply kept here and it slipped down. Now initial velocity is imparted. Fine. Find the normal force between the sphere and the particle just after the impulse. This part is very easy. This part A, is very easy. See, right at this point, there is a downward force mg. And there is a centripetal force. Let us call this point as point A. We have to write at A, downward gravitational force so downward centripetal force is equal to R. M v square by R. M v square by R. Now the point is, this mg, we write this way, mg provides the centripetal force and the balance is the reaction N, right? So, want to find out the normal force or normal reaction. Normal reaction is equal to mg minus m v square upon r. This part was easy, not a problem. Let's go to the second part. What should be the minimum value of v so that the particle do not slip from the sphere? Now, this force v that we have applied, velocity v, you can make it a small velocity, you can make it a big velocity, but what should be the velocity the particle does not slip, right? Does not slip, then mg will be equal to mv square by r. Because this normal reaction force, which is the balance, this force will try to lift the particle from the surface of the sphere. Is it clear? This normal force N, which is here, will lift the particle from the surface of the sphere, right? So, for no slipping, mg has to be equal to mv square by r. So, we write for no slipping, no slipping, mv square by r, m v, we write the minimum velocity v, mvm square by r is equal to mg. From here we get, from here, mm gets cancelled, we get vm square is equal to rg. And I think we should write right here, vm is the required minimum velocity. Minimum, that will make it clear, right? So v square, vm square is equal to rg, or we can write the minimum velocity vm is equal to under root the answer. This was the first answer. This is the second answer. Now there is a third part. It says that consider the initial velocity, that means velocity v here, is half of this minimum velocity, right? Then find the angle made by the radius through the particle with the vertical when it leaves the sphere. This part C is same as what we have done earlier. Let us say this is the angle theta when the particle leaves the sphere. That means from here, the sphere slips down. Let us consider this velocity is v1. And you know how to solve this equation. Very much you know, because here there is energy equation, there is one energy equation, and there is one force equation. Nothing more than that. So we can write the energy equation. Kinetic energy at A plus potential energy at A, this is the point A, will be equal to, and say this is the point P, when it slips, will be equal to kinetic energy at P plus potential energy at P. Just solve this equation. What is the kinetic energy at A? Is half m. Now this velocity in part C, we write the velocity it is given, the velocity given is half of this minimum velocity. The initial velocity is equal to Vm by 2. And for comfort in writing down the equations, we just give it a name. Say this is E. Say this is it. Therefore, so kinetic energy A is half m u square plus potential energy at A is mg, and this height is r, mg r, when it is all measured from this zero. This is the zero, say. This is the x-axis. mgr, this is equal to kinetic energy at P. Kinetic energy at P is half m v1 square, half m v1 square. Mind it, this is at this C part of this problem, it was initial velocity was u, Vm by 2. But when it reached the point P, its velocity is no more equal to Vm by 2. Its velocity is something else. Let us say this is V1. So we write half m V1 square plus what is the potential energy at P is m g r cos theta, because this side is r cos theta. This is r cos theta, right? Now from here we can write, now u is equal to Vm by 2. So here we write, we take okay, we write this way, but is equal to by 2, and Vm is given under root Rg. So it is under root Rg by 2. Therefore, square is equal to Rg by 4. If this is, say, equation A, then from equation A, we can write half m, u square is Rg by 4, plus mgr, this is equal to, and this is equal to half m v1 square, half m v1 square plus mgr cos theta, mgr cos theta, right? From here, all m gets cancelled. M, all m gets cancelled. And here we have Rg by 8. So if we say multiply both left-hand side and right-hand side by 8, multiply. Let's continue here. So from here we get, if I multiply, then it is equal to Rg plus this is Rg, so plus 8Rg plus 8Rg. Now this is gr cos theta, it will be multiplied by 8. So multiplied by 8 gr cos theta is equal to, this will be multiplied by 8. So we will have 4 v1 square. We will have 4 v1 square. From here we get 1 square, 4 v1 square is equal to Rg plus 8Rg, 9Rg minus 8Rg minus 8Rg cos theta. From here we get v1 square is equal to Rg upon 4 multiplied by 9 minus 8 theta, multiplied by 9 minus 8 cos theta, right? So say this is equation B. Now we have another part to work out. Let us make a bottom line of the board work here. The next part, and in the next part, what do we write? This is the energy equation at the point P. Now, I have told all of you repeatedly, you have two equations. One is energy equation, another is force equation. If you write the force equation at P, then centripetal force, we write at P, centripetal force mv1 square divided by r is equal to mg cos theta. That is mg downward and mg cos theta is the radial force available. And radial force mg cos theta provides the centripetal force mv1 square. So from here we get m gets cancelled, we get v1 square is equal to rg, v1 square is equal to rg cos theta. This is equation say C. Now from B and C, so we write from B and C, what we can write? Square rg cos theta, rg cos theta is equal to, here I have rg by 4, 9 minus 8 cos theta. This is rg by 4 into 9 minus 8 cos. All rg gets cancelled, rg gets cancelled. So what I have, cross multiply with 4. So I have 4 cos theta, 4 theta is equal to 9 minus 8, 9 minus 8 cos theta. So 4 cos theta, bring 8 cos theta to the left hand side. So you have then 12 cos theta will be equal to 9. From here we get cos theta is equal to 9 by 12, which is equal to 3 by 4. That is, or you can write theta is equal to cos inverse 3 by 4. So we have got the minimum velocity Vm, which is equal to under root rg. And if it initially starts from the point A with a velocity is equal to under root rg divided by 2, half of this minimum velocity, then at an angle theta, where cos theta equal to 3 by 4, this particle will slip off the sphere, right? Then now we shall go to the next problem solve.